Assalamu alaikum guys, my name is Sajid and in this explanation lecture I'll be going through the AS level physics 9702 paper 22 of the Fastpapers mock championship 2026. Okay. So let's start off with the first question. Complete figure 1.1 by putting a tick in the appropriate column to indicate whether the listed quantities are scalars or vectors. Well, acceleration is a vector because it has a direction. Objects accelerate towards some direction, right? So that's a vector. Since force is connected to acceleration, force is equal to mass times acceleration. Force, similar to acceleration, also has a direction. That's also a vector. Kinetic energy is a scalar. It does not have a direction. Okay, so momentum has a direction. This is a vector. Power and work, well, energy and work are the same thing. So they don't have a direction. Both of them are scalars. Power is also a scalar quantity. So vector quantities are acceleration, force, and momentum. Scalar quantities are kinetic energy, power, and work. A floating sphere is attached by a cable to the bottom of a river, as shown in figure 1.2. The sphere is in equilibrium with the cable at an angle of 75 degrees. So this right here, to the horizontal, assume that the force on the sphere due to the water flow is in the horizontal direction of water flow, okay? Radius of the sphere is 23 centimeters. The sphere is solid and is made of a material of density 82 kg per meter cube. Okay. Show that the weight of the sphere is 41. Right. So we have information about the density and the radius. So if we know the radius of a sphere, we also pretty much know the volume of the sphere. Volume of a sphere is 4 by 3 pi times r cube. And okay, so we need to find the weight, right? So let's find the mass first. The relationship between density, mass, and volume is rho is equal to mass over volume. We know the density, 82. Mass is unknown, the quantity we need to find. Mass. Now if we bring volume to this side of the equation, we simply multiply the density with 4 by 3 pi r cubed. 4 by 3 pi times the radius is 23. So 23 centimeters is the same as 23 times 10 to the power of minus 2 meters, which is 0.23. That gives us 0.23 cube. Okay, so mass would be, okay, so whatever the mass is, let's find the weight directly. Weight is equal to mass times gravitational acceleration. So that would give us a value of 4 over 3 times 0.23 cube times 82. Oh, there is a pi over there. It's time 22, 82 multiplied by the gravitational acceleration of 9.81 gives us a value of 40.997 something something, which can be rounded to 41. It's shown right here. The tension in the cable is 290 newtons. Determine the upthrust acting on the sphere. Right. Okay. So the sphere is in equilibrium. So the tension is basically balancing out the upthrust that's acting on the sphere. Let's draw a simpler diagram over here. Okay, let's consider that point, the sphere. It has an upthrust acting towards the top and a force that is acting downwards, which is balancing the upthrust. And we have the tension acting at 75 degrees to the horizontal. 75, right? Yeah, it is 75. Okay. So this vertical force right here is the vertical component of the upthrust, which has a value of, okay, so this right here is the opposite of the angle, this side right here. If we draw a right angle triangle where the hypotenuse is 290, the angle being 75 degrees, this would be sine 75. Sine of 75 times 290 degrees. That's the vertical component of the tension. So upthrust is equal to the vertical component of the tension let's call it TV, vertical component of the tension, plus the weight of the sphere. We already know the weight of the sphere as 41, which gives us a value of 290 sine 75 plus 41. That gives the value of upthrust as 321.118 something something. We can round it to 321. 321 newtons. The unit is already given here, so we don't need to write a newton here. Explain the origin of the upthrust acting on the sphere. Okay, so upthrust originates from the difference in pressure between the bottom surface and the top surface of the sphere. So the pressure at the bottom surface of the sphere is obviously greater than the pressure at the top surface. The pressure at the top surface is simply atmospheric pressure, and the pressure at the bottom surface is density of water times gravitational acceleration times depth. So that pressure is greater than the atmospheric pressure, which is the origin of the upthrust. The answer would be something like this. Okay, now if the situation was like this, let's say this is the water surface and this is the water bed. If a sphere is floating somewhere between these two, the origin of the upthrust would be the difference in pressure between the top and the bottom surface, similar to before. So this happens because the pressure, hydrostatic pressure or pressure exerted by a fluid, increases with depth. So the pressure exerted over here is greater than the pressure exerted at the top, which is why there is a net force upwards, and that upward force is upthrust. Question 2. A man wearing a wingsuit glides through the air with a constant velocity of 47 meters per second at an angle of 24 degrees to the horizontal. The path of the man is shown in figure 2.1. The total mass of the man and the wingsuit is 85 kg, 85 kilograms. The man takes a time of 2.8 minutes to glide from point A to point B with reference to the motion of the man. State and explain whether he is in equilibrium. Okay, so whether he is in equilibrium. Now, the man glides through air with a constant velocity, right? So constant velocity means there is no acceleration. If there is no acceleration, there is no resultant force. And if there is no resultant force, whatever is traveling at constant velocity is in equilibrium. The answer would be something along these lines. For the movement from the man from A to B, determine the decrease in gravitational potential energy. Okay, so the man goes from A to B and the height decreases by h. Okay, so gravitational potential energy is mass times gravitational acceleration times change in height. So we already know the value of mass, 85 kg. We know gravitational acceleration, so we need to find how much the height changes. Okay, so the distance between A to B is unknown, but we know the uh, velocity of this man. Velocity at an angle of 24 degrees. If we know that velocity, we can find out the vertical component of that velocity. So if the hypotenuse is 47, the vertical component of velocity would be 47 sine 24. Sine 24 because the vertical is the opposite of this angle. 47 sine 24 is the vertical velocity. Now vertical velocity multiplied by time, because distance is equal to velocity times time, right? So we multiply time with the vertical velocity to get the change in height, h. So the time taken is 2.8 minutes. If we convert that to seconds, we get 2.8 times 60. This is the change in height. So change in gravitational potential energy would be mass times gravitational acceleration times change in height, which is 85 times 9.81 times 47 sine 24 times 2.8 times 60. That gives us a value of approximately 2.68 times 10 to the power of 6. 2.68 times 10 to the power of 6. The unit is already given here, so we don't need to write the unit. The magnitude of force on the man due to air resistance. Okay, so the man loses a total of 2.68 times 10 to the power of 6 joules of energy, right? And he travels a distance of A to B, whatever that distance is. Now, energy is force times distance. We need to find the force, so force would be equal to the energy over distance. The amount of energy he lost is 2.68 times 10 to the power of 6, the same as this value here, over the distance. Okay, now the distance covered from A to B is simply the speed of this man multiplied by the time taken, which is 2.8 minutes. Very straightforward. 2.8 minutes times 60 seconds, which gives us a value of, oh, we need to multiply the speed here. I forgot about that. Speed times the time. And the value of this is 339 point something something. We can simply round it to 340. So the force would be 340 newtons. The pressure of the still air at A is 63 kilopascals and at B is 92 kilopascals. Assume the density of the air is constant between A and B. Determine the density of the air between the 2 points. Okay, so at point A, the pressure is 63 kilopascals, and at B it's 92 kilopascals. Now, pressure of any fluid, not just water, not just liquids, the pressure of air as well depends on height. So the equation that we normally use, rho times g times h, density times gravitational acceleration times the change in height. This is the equation we use normally for liquids, right? The same thing can be applied for air as well, or any gas. So the pressure over here is different from the pressure over here, and the difference arises from the difference in height, which means density times gravitational acceleration times the change in height will be equal to the change in pressure, which is 92 kilopascals minus 63 kilopascals. So we convert kilo to regular pascals, so we need to multiply it by 10 to the power of 3. The density of air is what we need to find. Density will be equal to the change in pressure, 92 minus 63 times 10 to the power of 3 over gravitational acceleration of 9.81 times the change in height. Now, the change in height would be exactly what we found over here. This is the vertical distance, or the value of h. 47 sine 24 times 2.8 times 60. So we simply plug in the value of that, the one we just saw over here. 47 sine 24 vertical component of speed, velocity, multiplied by the time, 2.8 times 60, which is approximately 0.9204 and so on. We can round it to 0.92. So the density is 0.92 kg per meter cube. Right. Question 3. A wire is fixed at one end so that it hangs vertically. The wire is given an extension x by suspending a load F from its free end. The variation of F with x is shown here in this figure. The wire has cross-sectional area of 9.4 times 10 to the power of minus 8 meters square and original length of 2.5 meters. Describe how measurements can be taken to determine accurately the cross-sectional area of the wire. Okay, now this here is a very common question. So to determine the cross-sectional area, what you need to do is use a micrometer screw gauge or a vernier caliper. Preferably a micrometer screw gauge, because micrometers are more precise, they have a higher precision. So use a micrometer screw gauge to measure the diameter of the wire at multiple points along its circumference. So if this is the cross-section of the wire, you determine using a micrometer screw gauge the diameter along one point, along another point over the circumference, and, well, basically multiple points along the circumference. So you have multiple values of diameter like that. You take all those values and then average them to find the average diameter, and then apply the equation pi times r square, or pi times d over 2 whole square, which gives you the cross-sectional area. Determine the Young modulus E of the material of the wire. Okay, so Young's modulus E is stress over the strain. Stress is force over area and cross-sectional area, and strain is extension over the original length. If we rearrange this equation, we get force times original length divided by extension times cross-sectional area. Okay, now we already know the original length and cross-sectional area. They've already given us these two values. Force over the extension, if you check this graph, the y-axis is force and x-axis is the extension. So the gradient of this graph is y over x, change in y over change in x, which is basically the change in force over change in extension. Since the graph starts at 0, 0 at the origin, the gradient is simply force over extension. So we can replace the force divided by extension part of this equation with the gradient. Gradient times length over area. Okay, so the gradient of this line is 4 divided by 0.8. So 4 newtons divided by 0.8 millimeters extension. Force over 0.8, converting this to meters, times 10 to the power of minus 3, times the original length is 2.5, and the cross-sectional area is 9.4 times 10 to the power of minus 8. 9.4 times 10 to the power of minus 8. Okay, that gives us a value of pascals. The wire is replaced by a new wire of the same material. The new wire has twice the length and twice the diameter of the old wire. The new wire also obeys Hooke's law. On the figure, sketch the variation with extension x of the load F for the new wire from x equal to 0 to x equal to 0.8 millimeters. Okay, now the Young modulus is a property of the material itself. So the value of Young modulus does not change. So Young modulus being constant, it's constant, right? So this value is equal to force over the extension times length over the area, which is not approximately, it is equal to the gradient of the graph multiplied by the length. Okay, now we are increasing the length by 2, right? Increasing the length by 2. And if we are increasing the diameter by 2, by twice, so it has twice the diameter, right? Which means the same wire will have 4 times the cross-sectional area, because, well, area is something something times d squared, right? So if diameter increases by 2 times, area will increase by 4 times. Okay, 40. Right. Now, to keep the Young modulus constant, the gradient of this line has to be doubled. Why? Because 2 over 4 gives us 1 over 2. So half times length over diameter. So if we want to come back to this equation right here, the initial equation, we need to cancel out this half somehow. And the only way to do it is to multiply the gradient by 2, which means the new graph will have twice the gradient. Okay. It starts from the origin, and now for the same extension, twice the load will be required. So the load here will be 8. Now, I don't have a rule, but basically we need to draw a straight line from the origin to this point, 8, 0.8. Let me try to draw a straight line as best as possible. Yes, something like that. You get the point, right? So a straight line from the origin to the point 808. Okay, question 4. A cylinder is made from a material of density 2.7 grams per centimeter cube. The cylinder has diameter 2.4 centimeters and a length 5 centimeters. Show that the cylinder has weight 0.6 newtons. Okay, so the cylinder has a diameter of 2.4. It's the diameter, so from here to here, 2.4 centimeters. And the height of the cylinder or the length is 5 centimeters. So the volume would be pi r square, because it's a circular cross-section, the cross-sectional area multiplied by the height. So the radius would be 2.4 centimeters. Converting that to meters gives us 2.4 times 10 to the power minus 2 over 2. 2.4 centimeters is the diameter, and 2.4 over 2 centimeters is the radius. So pi times radius square times 5 centimeters. There's no space, so let me write it down here. 10 to the power minus 2. This quantity right here is the volume of the cylinder. Now, density is mass over volume. We need to find the weight, right? So the weight is mass times gravitational acceleration. So mass times gravitational acceleration would be, if we bring this volume to the other side of the equation, it becomes density times volume times gravitational acceleration of 9.81. So this gives us a value of 2.7. Actually, this is in grams per centimeter cube, so we need to convert that to kg per meter cube. So 2.7 grams is 2.7 times 10 to the power of minus 3 kg. And 1 centimeter cube is 1 times 10 to the power of minus 2 meters cube. Okay, times the volume. The volume is pi times 2.4 times 10 to the power minus 2 over 2, the radius, square times the height, 5 times 10 to the power minus 2. A lot of conversions here. So that gives us an answer of, okay, we forgot to multiply the 9.81 here times 9.81. Let's make a separation over here. That gives us a value approximately 0.60 newtons. Okay, in case anyone is confused, right over here, we converted the density to kg per meter cube. So 1 gram, or let's say 2.7 grams, is 2.7 times 10 to the power of minus 3 kilograms. So if we multiply it by 10 to the power of minus 3, we're converting 2.7 grams to 2.7 times 10 to the power of minus 3 kilograms. And 1 centimeter cube, okay, 1 centimeter is 1 times 10 to the power of minus 2 meters. So 1 centimeter cube would be 1 times 10 to the power of minus 2 whole cube, meter cube. Okay, so that's the entire conversion over here. The rest are pretty simple. 2.4 centimeters has been converted to meters by multiplying it with 10 to the power minus 2. And the denominator of 2 is given here because 2.4 is the diameter. So we're converting this to radius. So pi times the radius squared times 5 centimeter is the length of the cylinder, or the height of the cylinder. So we multiply 5 with 10 to the power minus 2 to convert this to meters. And the 9.81 is to find the weight from the mass. The cylinder in A is hung from the end A of a non-uniform bar AB. As shown in figure 4.1, the bar has a length 50 centimeters and has weight 0.25 newtons. The center of gravity of the bar is 20 centimeters from B. The bar is pivoted at P. The pivot is 12 centimeters from B. Okay. An object X is hung from end B. The weight of X is adjusted until the bar is horizontal and in equilibrium. Calculate the weight of X. Okay, a lot of moments going on here. So let's calculate the clockwise moment over here first. So the clockwise moment would be the weight of X multiplied by the distance. Force times distance. So the weight of X times 12. This moment is being balanced out by the anti-clockwise moment on the left side of the pivot. This will be equal to the weight of the cylinder, 0.6, times the distance from A to the pivot. The distance from A to the pivot will be 50 minus 12, because 50 centimeters is the length of the bar, and the pivot P is 12 centimeters from B. So the distance here would be 50 minus 12, plus moment exerted by the weight of the bar itself, 0.25 times this distance right here, which is 20, 12 subtracted from 20. If we make x the subject, we get this entire thing over 12. That gives us a value of approximately 2.07 newtons. 2.07. The cylinder is now immersed in water as illustrated in figure 4.2. An upthrust acts on the cylinder and the bar is not in equilibrium. Explain why the weight x must be reduced in order to obtain equilibrium for AB. Okay, so upthrust acts on this cylinder, which means there is now a clockwise moment applied on the left side of the pivot, which means the bar that was previously in equilibrium is now not in equilibrium anymore. We need to reduce the value of x so that the clockwise moment over here decreases. State the principle of conservation of momentum. Okay. So the principle of conservation of momentum states that momentum before a collision and momentum after a collision are both equal. So momentum is conserved. Momentum before collision is equal to momentum after collision in an isolated system. So another way to state the principle is by saying the total momentum, the sum of momentum, is conserved for an isolated system. Isolated system refers to systems where no external force is applied. A stationary firework explodes into 3 different fragments that move in a horizontal plane as illustrated in 5.1. The fragment of mass 3m has a velocity of 7 meters per second perpendicular to line AB. It's going upwards, which means it has no horizontal momentum. Fragment of mass 2m has a velocity of 6 meters per second at an angle theta. To line AB, fragment of mass 1.5 m has a velocity 8 meters per second at an angle theta to line AB. Okay. Use the principle of conservation of momentum to determine theta. Okay, so one thing we can do is we know that this fragment right here, the fragment with 3m mass, has no horizontal momentum, which means the momentum of the 1.5 m mass will be equal and opposite compared to the momentum of the 2m mass. Okay, so we now need to find the horizontal component of these two momentums. The horizontal component of this would be, we have an angle theta over here. This right here is the hypotenuse. If we consider this a right angled triangle, this line here would be 6 meters per second times cosine of theta multiplied by the mass 2m. This is the horizontal component of the mass on the left side over here, bottom left. And the horizontal component of this is similarly 1.5 m times 8 cosine of theta. These two will be equal. So 2m times 6 cosine of theta is equal to 1.5 m times 8 cosine of theta. Now, we have cosine of theta on both sides of the equation, which kind of defeats the purpose. So what we should do here is compare the vertical components of the moments, which means the total vertical momentum towards the bottom will be equal to the total vertical momentum towards the top. So that means we can discard this. 7 multiplied by 3m, which is pretty straightforward because the 3m mass is not moving at an angle, it's moving vertically upwards, perpendicular to AB. This momentum is equal to the momentum downwards, which is 2m times 6. Okay, if cos theta was the horizontal momentum, sine theta will be the vertical momentum plus okay. Now we can cancel out all the m's that we have here. That only leaves us with theta. If we solve this equation, theta would be around 61 degrees. So the theta, value of theta is 61. Calculate the ratio kinetic energy of fragment of mass 2m over the kinetic energy of fragment of mass 1.5 m. Okay, so kinetic energy is half times mass times velocity squared. So let's consider that m1 or v1. Okay, you know what? Instead of writing m and v, let's just put in the mass and the velocity of the fragments. The fragment of mass 2m of course, has a mass of 2m times the velocity square. Velocity is 6. Actually, it's not the velocity, it's the speed. Kinetic energy is a scalar quantity, so we don't need to worry about the direction here. So times 6 squared divided by half times 1.5 m times 8 squared. 8 squared. So we can get rid of the half and the m's here, which leaves us with a ratio of 1 over 4, 3 over 4, which is 0.75. So the ratio would be 0.75 or 3/4. Number 6. Two coherent waves, x and y, meet at a point and superpose. The phase difference between the waves at the point is 180 degrees. Wave x has an amplitude of 1.2 centimeters and intensity I. Wave y has an amplitude of 3.6 centimeters. Calculate in terms of I the resultant intensity at the meeting point. Okay, so at the meeting point, x and y meets with a phase difference of 180 degrees, right? So if this right here is wave y, wave x will be at a phase difference of 180 degrees, and it has a smaller amplitude, so it's going to be something like that. This right here is wave x. Wave y has an amplitude of 3.6 centimeters, and wave y has an amplitude of 3.6 centimeters, wave x has an amplitude of 1.2 centimeters. So the resultant amplitude would be 3.6 minus 1.2. Let's call this amplitude resultant, AR, which is 2.4 centimeters. Now, the relationship between intensity and amplitude is that intensity is directly proportional to amplitude square, which means intensity over amplitude square is a constant. Let's call it K. Now, this also means the resultant intensity, let's call that IR, over the resultant amplitude, which is 2.4 centimeters square, will be equal to the intensity of x over the amplitude of x, 1.2 square. So the resultant intensity IR will be equal to I intensity of x times 2.4 squared over 1.2 squared. Now if you compute this, you get a value of 4, and I stays as I. So the resultant intensity is 4 times the intensity of x. Monochromatic light is incident on a diffraction grating. Describe the diffraction of light waves as they pass through the grating. It's quite simple. When light passes through a slit, they simply spread out. Nothing to overthink here. So when light or any wave passes through a slit, they simply spread out. A parallel beam of light consists of two wavelengths 540 nanometers and 630 nanometers. The light is incident normally on a diffraction grating. Third order different diffraction maxima are produced for each of the two wavelengths. No higher orders are produced for either wavelength. Determine the smallest possible line spacing d of the diffraction grating. Okay, so to answer this question, we simply use the equation n lambda is equal to d sine theta. N is the number of order. In this case, the third order is the maximum order that is produced for both of these waves. So n will be equal to 3 times lambda. We have two different values of wavelength, so we'll find the distance d for both of these wavelengths first. is equal to d times sine. Okay, so the angle theta will be 90 degrees. Why 90? Because third order diffraction maxima are produced for each of the two wavelengths and no higher orders are produced, which means third order is the maximum number of orders that are produced in this scenario. No higher order is produced. So the highest order has an angle of 90 degrees. Sine 90 is 1, so we can simply remove it from the equation. D, the value of D will be 3 times the value of lambda. Lambda is 630 nanometers in one of the scenario. D is 3 times 540 nanometers in another scenario. 3 times 630 gives us 1890 nanometers, and in this case D is 1620 nanometers. Right, now from these two lengths, if we have a line spacing of 1890, we get a third order diffraction maxima for the 630 nanometer wavelength of light. But if we reduce the value of D even further down all the way to 1620, we will get a third order diffraction maxima for the 540 nanometer wavelength of light, but we won't get a third order diffraction maxima for the 630 nanometer light anymore. So the smallest possible length would be 1890. 1890. Since this value is in nanometer, we multiply it by 10 to the power of minus 9 to convert it to meter. Question 7. A wire has a resistance of 1.8 ohms. The wire has a uniform cross-sectional area of 0.38 millimeters square and is made of a material of resistivity 9.6 times 10 to the power of minus 7 meter ohm meter. Calculate the length of the wire. Okay. So the relationship between all of these quantities is resistance R is equal to rho L over A. Rho is the resistivity, L is the length, and A is the cross-sectional area. So the resistance is 1.8, resistivity is 9.6 times 10 to the power minus 7 times L, length is the value we're trying to find, over the cross-sectional area, which is 0.38 millimeter square. We need to convert this to meters. That gives us times 10 to the power minus 3 whole squared. If we make L the subject, L is going to be 1.8 times the cross-sectional area over the resistivity of the wire. If we plug in the values of A and rho, we get 0.7125. We can round that to the nearest two significant figures. That gives us 0.71 meters. A resistor X of resistance 1.8 ohm is connected to a resistor Y of resistance 0.6 ohm and a battery P. As shown here in this figure, the battery P has an EMF of 1.2 volts and negligible internal resistance. Explain in terms of energy why the PD across resistor X is less than the EMF of the battery. Okay, so we have two resistors X and Y, which means some of that energy is dissipated, some of the energy provided by the supply is dissipated across X, and the other portion is dissipated across Y. So the answer would be calculate the PD across resistor X. Okay, so we can simply apply the potential divider rule here. So the ratio of resistance X over the total resistance is equal to the potential difference across X over the total EMF. Okay, so if we plug in the values, resistor X is 1.8 and the equivalent resistance is, since they're both in series, it'll be 1.8 plus 0.6. Now, if we bring the EMF to the left side of the equation, we simply multiply this ratio with the total EMF times 1.2. That gives us the value of Vx, which is the potential difference across X. Solving this equation gives us 0.9 volts. Another battery Q of EMF 1.2 volts and negligible internal resistance is now connected into the circuit of figure 7.1 to produce a new circuit shown here. State whether the addition of a battery causes the current to decrease, increase, or remain the same in resistor X, battery P. Okay, previously we had just our battery P. Now we have a battery Q with the same voltage. Okay, now since the voltage remains constant, the current, since the voltage remains constant, the current that's flowing through this section of the wire will still be the same. But now, unlike previously, this current, the current with a value of I, is provided by both of these batteries. So battery P will provide a portion of that current, battery P will provide a portion of that current, and battery Q will provide another portion of that current. So the current provided by battery P is now less than it was before. The circuit shown in 7.2 is modified to produce the new circuit shown in 7.3. The total resistance of the two resistors connected in parallel, so 3.6 and 1.8. Okay, so if we have two resistors connected in parallel, let's call this R1, let's call this R2. The equivalent resistance, RT, can be calculated using this formula. R1 times R2 over R1 plus R2. How? Because, well, let's use the usual formula. 1 over RT is equal to 1 over R1 plus 1 over R2. Okay, so if we make the denominators equal, we get R1 times R2. And over here on the numerator, we get R1 plus R2, because we need to multiply 1 with R2, and we need to multiply this one with R1 to make the denominators consistent. This is the value of 1 over RT, which means RT, the total resistance, would be R1 times R2 divided by R1 plus R2. Let's keep that to the side. This is a simple formula that you can use for two resistors in parallel instead of going through the usual process. Anyways, we can use both, right? So if we use this formula right here on this equation, for this question, we get 3.6 times 1.8 divided by 3.6 plus 1.8, 1.2 ohm. Compare an alpha particle with a beta particle in terms of their masses and charges. Okay, so a beta particle is simply a positron, and an alpha particle is made of 2 protons and 2 neutrons. Okay, so let's consider this an alpha particle, and let's consider this dot right here a beta plus particle. An alpha particle has a mass which is much greater than the mass of a beta plus particle or a positron. They both have equal charge, not equal charge, they both have charge of the same sign, positive charge, but the charge of an alpha particle is twice the charge of a beta particle, beta plus particle. So the answer would be something along these lines. In this answer, E refers to the elementary charge. Nucleus P undergoes alpha decay to form nucleus Q. Nucleus Q then undergoes a further decay to form nucleus R. The proton and nucleon numbers of P and R are shown. On 8.1, draw a cross to show the proton number and nucleon number of Q. Okay, so P undergoes alpha decay to form Q, which means P, after undergoing alpha decay, will have 4 less mass. So from 216, it'll go down to 212 over here. It will also have 2 less protons, which means from 84, it'll go down to 82. Okay, so that is the position of atom or nucleus Q. State the names of the particles emitted as Q decays to form R. Okay, so they have the same mass, but the proton number increases by 1. So if the mass remains the same for beta plus decay and beta minus decay. For beta plus decay, the resultant nucleus will have 1 less proton. And for beta minus, the resultant nucleus will have 1 more proton. So the decay from Q to R is caused by beta minus decay. So the name of the particle would be an electron or beta minus. You can write beta minus, or you can also write the beta symbol minus, or you can also write an electron. Now, whenever beta particles are emitted, whether it's beta plus or beta minus, an antineutrino is also emitted in the case of beta minus. In the case of beta plus, a neutrino is emitted. So the particles will be, number 1, a beta minus particle. The other particle would be an antineutrino. Before the alpha decay, P is traveling at a constant velocity. After the decay, Q has a velocity of 1.3 times 10 to the power of 5 meters per second at an angle of 68 degrees to the original path of P. The alpha particle has a velocity of 150 times 10 to the power of 5 meters per second at an angle of 25 degrees to the original path of P. As shown here, calculate the kinetic energy of the alpha particle. Okay, so the kinetic energy will be simply half times the mass of an alpha particle. Okay, so an alpha particle is made of 2 protons and 2 neutrons, right? So the total mass would be 4 nucleons, which is 4 times the atomic mass unit, U. So half times the mass is 4U times velocity square is 150 times 10 to the power 5 meters per second whole squared. 1U has a mass of, the mass is shown here in the data, 1U has a mass of 1.66 times 10 to the power minus 27. Kilograms. So if you simply plug in the value of this over here in the place of U, the kinetic energy will be approximately 7.5 times 10 raised to minus 13 joules. So the kinetic energy is 7.5 times 10 raised to minus 13 joules. All right, guys, so that concludes this paper. Wishing you all the best for your exams.